Nicholas and everybody in our new webinar in SPWLA Iraq. Thank you for watching.
Yes. Thank you, Dr. Mohammed.
Thank
Okay.
you.
Okay. Thank you for attending. So let me start. Okay. So the recording is start and the webinar will start by now. My name is Mazen Hilali. I'm senior geoscientist working for local oil in Iraq in South Iraq on West Gurna 2 project recently. Uh, let's say nowadays, not recently, since 3 years. And our series for this year will be like focus on integrity. This is our second webinar for this year. Mr. Nicholas Cutler, he's domain champion, expert in production logging, Sigma, cement log, MFC, whatever is related to cased hole logging. He will give us today a webinar regarding casing inspection. Uh, just I will make few slides. Is my screen sharing for you, Nicholas? You can see.
Yes, we can see your screen. We can see your Teams now. Okay, now we can see your
No.
presentation. Good.
Okay. So the theme for this year will be the focus of integrity. Today will be like casing inspection by Kappa Engineering Company. What we plan to do this year, like we have planned for 8 webinars. Already did one with a TGT company. Today webinar will be with Kappa Engineering, as we previously mentioned, regarding casing inspection, and we expect more, a webinar per each, one webinar per each month. Okay, next will be also from TGT regarding tube integrity, cement evaluation by Kappa Engineering using Emerald software. We'll have also like some webinar regarding the tool themselves, like what we did with TGT, like from EVCAM, also about software from GeoActive by IP software, and we'll have also like high temperature well evaluation using scientific drilling tools. Okay, for question and answer, it will be at the end of lecture. It's not like so not interrupt the webinar sequence. Okay, and I will give the sharing right now to Mr. Nicholas. Nicholas, you can share your screen.
Perfect. Thank you, Masin. I'm starting to share my screen. Please confirm if you can see my screen.
Yes, yes.
Okay, excellent. Okay, so let's get started. So first of all, welcome to today's webinar, and thanks Masin and SPWLA Iraq for this invitation. I'm honored to be here today. So as Masin mentioned, today's webinar will be on casing inspection using Emerald. Right, Emerald is our case hole logging software. My name is Nicholas Kotler. I'm based in Bahrain, right? And I'm Emerald Product Champion. So we will go straight to some examples in how to diagnose different well problems in Emerald, right? But before that, I will do a very quick introduction. In this case, in this webinar, we will deal with multi-finger caliper and spectral noise logging data, right? So just to give you a brief intro of the data that I will load in Emerald, I will show you some slides. So many of you might be familiar with let's say the star of the day, that is the MFC tool. Here, what you see in this picture is a 60-finger caliper. And essentially, these tools contain an array of independent fingers, meaning that each finger will measure a radius value independent of the of the other fingers, in contrast to what is an XY caliper, right? The tool only records in up passes, so you run and hold the tool with the fingers closed, then a motorized section open the fingers, and it records only in up passes. So compared to other case hole logging techniques like production logging, what you will notice is a very fine sampling rate. In production logging, we typically record like 2 points per foot, something like that. Here we record 100 points per meter or 100 points per feet, per foot, right? So files are typically quite big. And I mentioned in this case 60 finger caliper. The number of fingers has to do mainly with the tool, the pipe diameter to be logged, right? So in this case, actually, the example that we will see this webinar is a 5.5-inch casing. So a 40 finger caliper will be used, right? Then the finger response itself, what we want to measure are these changes in internal radius, either as you see here, a hole, a penetration, right? Some metal loss due to corrosion, erosion, or also the other way around, deposition, right? And for that, each finger is connected with an actuator, and this actuator will move in and out of a system of coils, a displacement transducer, and this will allow us through some surface calibration, right? This will allow us to quantify the radius and the radius variation as the tool records the up pass. So multi-finger caliper is, let's say, I would say personally, is the star. Let's say, is the bread and butter of the integrity evaluation. And why is that? Remember, compared to other techniques, that multi-finger caliper deals with the first barrier, right? We need to be in touch with the tubing or in the casing that we want to analyze. And this is important because if you see, well, there are two studies here. I know that they are a bit old, but this is the published data that I could find. For example, this is from Norway. And if you see all the failures found in Norway, I think these are 100, like 200 wells, something like that. You will see that the main issues occur in the tubing. Right here, you can see the tubing. So, or typically when the well experience annular pressure between casing and tubing, right? And also the casing. The valves, right? So something that can get in touch with that first barrier could be able to diagnose a large proportion of problems occurring in tubing and casing, right? Similarly, this is another statistic from Gulf of Mexico, and you can see the number of wells with sustained casing pressure, and these are really like 11,000 casings suffer from sustained casing pressure. So these are real issues, right? And most of the issues, more than 50%, occur in the production casing, right? So between tubing and production casing is the sustained casing pressure. So you can imagine that a tool that get access to that first barrier, either the tubing or the casing, depending on your well completion, will deal with with a large percentage of the problems found in wells worldwide. So, but this is not the only, let's say, type of problems, leaks that may cause annular pressure. But here you can see the typical problems that could be diagnosed through multi-finger caliper, right? So in the first case, you can see a tubing that has suffered from corrosion in this particular case with some fully penetrating holes, right? So definitely, if this is an injector well, the water would not be going to where we expect, or if it's production, of course, this will result in annular pressure, right? Mechanical failure, in this case, what you see, this is a casing burst, right? So this is when the hoop stresses are larger than the let's say the burst pressure of the casing. Deformation mechanisms, in this case, you can see a 3D image of a helical buckling, right? Compressional stresses or tectonic movements across faults may cause different type of deformation, shear deformation, helical buckling, bands, and so on. Casing wear, right? Imagine that you set your casing and then re-enter the well to perform, to further drill or coil tubing or any intervention. The contact forces between the BHA and the drill pipe itself can leave groups, reducing the mechanical properties of the casing. And also deposition, right? Deposition is another type, calcium carbonate, asphaltenes, and so on, right? These are all problems, integrity issues that may be that can be diagnosed through multi-finger caliper. So with this quick intro, I will go straight to Emerald. In Emerald, what I'm going to do is we're going to deal with a casing that has a leak, right? And we are going to use two tools to find this nick. So first, we will do it through a multi-finger caliper, and then we will move to the spectral noise data. Before going to spectral noise, I will get back to some theory, right? So I see someone saying that cannot see the screen. If you can, please, the rest of you can confirm that you can see the screen before I move on, just to avoid any issue.
Yeah, for me, I can't see the screen.
Okay. So, okay. So this is Emerald. What I'm going to do, I'm going to start a new file from scratch, and we'll start by creating a survey that I will call it MFC, for example, main pass. Right? We're going to load some multi-finger caliper data here. I will go straight to, typically we would like to define the more well information that we have, completion, open hole logs, well diagrams, that the better, right? But in this case, we're short of time, so let's go straight to load, and we're going to load multi-finger caliper MFC 40. This is an LAS file that typically contains, as you see here, one radius track, one radius column for each finger, right? And also contains some
Sorry.
deviation.
Yeah,
Yes.
I saw in the update, the new one, it's mentioned that right now the updated version have fixed some problem regarding the loading. The loading become much easier.
Yes. Before you had to. So first of all, yeah, the data in 550, the multi-finger caliper data may be loaded as DLEs, but also before you had to identify some mnemonics. Now it's everything in one go. If you see, I loaded the data and I didn't have to identify anything, so I just click import and everything gets loaded immediately, right? So. There we go. So we are loading this data, and you can, as I said, these are big files because the sampling rate is, we have 100 points per foot in this case. So you can see in the background some data has been loaded, and many of the statistics that we are interested are a function of the nominal diameters, right? So here I go in the multi-finger caliper information, I go to the diameters tab, and from the catalog, I will find the pipe size, the casing or tubing size that I'm interested in. In this case, it's a 5.5 inch, 17 pounds per foot. I click OK, and there we go. So as soon as I accept this, you can see that Emerald will compute a number of statistics, right? So this is all our data loaded. And as I said, Well, first of all, let me start from the left. We have a number of, cable speed, deviation, and so on that I will remove from this view initially. And then there are some there is the typical unwrapped image of the multi-finger caliper, and then the statistics, ovalization. The well-knowns are penetration here, reduction, metal loss. These are the ones that we are interested. Remember that we are looking for a leak in this case. So what we are looking is a high penetration, 100% penetration, right? Means that we have a fully penetrating hole. So what,
Sorry,
but
Nicolas.
yes.
Just I want to confirm the screen is sharing for everybody else. Dr. Mohammed, you can see the screen as well?
Yes, Mr. Mazen. Everything
Ah,
is okay.
okay. So I believe somebody is, it's Mr. Ahmed. He say he cannot see the screen. I believe this is something wrong with his MS team or the internet. And we will share the recording for the people that have such technical issue in all cases. Thank you.
Okay, good. So the first thing, so if you see, this is the multi-finger caliper. This is the unwrapped image of the multi-finger caliper. So unwrapped, what we do is the center of the image is low side, right? Low side of the if of the cross section, and the sides of the image are the high side of the cross section, right? So, and if you see in this case, what we is like we see blue, so smaller radius on the bottom of the cross section and larger radius on the high side. Right, so this is telling us if you haven't seen raw data, you may think, okay, maybe the well has some deposition and some penetration, but this is a very typical problem called not a problem. This is a feature of multi-finger caliper logs that is the eccentricity, right? So we will fix that. So I'm going to go to the well integrity tab. The well integrity contains all the, if you see here, multi-finger caliper, cement, thickness, and noise options of Emerald, and I'm going to launch the multi-finger caliper processing, right? So just this is the processing window, and as I said, you can, for example, I'm going to zoom in at certain depth here with the scroll, and um, if you see here, I'm going to click on cross section and show you the cross sections at certain depth, and I'm going to add the markers. The markers here are the position of the fingers, right? So there are 40 fingers. If you hover over a finger, you can see the finger number 18, the angle, and the radius, right? So can you see that compared to the nominal diameters in gray here, this is a nominal pipe wall, seems like we have some penetration on the high side and some deposition on the lower side. Actually, let me remove this. So can you see that the multi-finger caliper sees a circular profile, but this is not concentric with the nominal pipe diameters, but actually there is an offset, right? And this is because, let me show you quickly here, the tool, if it was a perfectly vertical and centralized well, this is a multi-finger caliper, which is always run in between strong, like at least 20 or 30, 35 pounds of force of centralization, right? In this case, if it's perfectly centralized, the multi-finger caliper should be concentric with the pipe, and therefore all the measurements should be at the same level. But what happens as soon as we have a bit of deviation, due to the MFC and tool string weight, the tool moves down, right? And this is what we see now. So the fingers pointing up show a higher radius than the fingers pointing down, right? So that's why it looks like we have penetration and deposition at the same time. In reality, it's none of that, but is this centralization, right? So what I'm going to do, the first thing here is to centralize the data. Centralization basically, I'm going to, so what the centralization does is recomputes the finger radius after finding what is the actual center of the pipe, right? So the fingers right now, the center of the finger is are from here, from the center of the MFC, but the center of the pipe is here, right? So what we need to do is recompute the radius based on the actual center, right? So this is a geometrical algorithm. I'm going to launch it later on in the, I cannot spend much time with this, but later on, if you have questions about the centralization algorithm, please let me know, right? If you see here in the background, it says outliers. Of course, we need to exclude a number of outliers. If we have penetration or deposition, this will affect the shape of the perfect circle or ellipse that we use. So we remove these outliers from the centralization, and then we after that we take them into account for the final results, right? So here is the centralized data comparing to, if I go back to cross section here, can you see now that the radius data in red and some points in blue, these are the ones that were excluded during the centralization, are now pretty much at measuring the same radius as the nominal ID. This is basically the data that we are going to use for for the final results. But this is not the end of the story, but because can you see here now the centralized data has like these bands like this. It looks like spaghetti of darker blue, right? So you may wonder, what is this? Is this actual features of the well, some scratch on the pipe, or some deposition? The data right now is corrected, is oriented using a relative bearing device. So first of all, what I'm going to do is uncheck the bearing, right? I'm going to uncheck the bearing, and then if I uncheck the bearing, the map is basically showing for finger 1 on the left to finger 40 on the right, right? So this you can see now some vertical stripes. So if this occurs, it's telling us that the finger is consistently measure larger or smaller values from the top of the log interval to the bottom, meaning that is a problem with the finger itself. It's not a problem with the well. So this is related to the initial calibration, meaning that we need to recalibrate the fingers, right? So here there are some recalibration options, and actually you can do it interactively as well, recalibrate, interactive. I'm going to select an interval for recalibration, for example, up here, and I'm going to compare the individual fingers value to the median in this particular range. And when I do this, the recalibration is in progress now. And then you can see now recalibration has finished. And then you can see that the vertical stripiness initially present is gone now, right? So meaning that the data is more homogeneous, right? Some shifts were applied to the individual finger values based on the median of all 40 fingers along that across that interval that I selected, right? So now the data is ready, right? So now the statistics computed, they were already computed automatically by Emerald. So let me show you. If you click here and show, you can see the metal loss, for example, or the penetration like this. Here we are. So I'm going to zoom in, for example, on the metal loss, and this is the penetration. These are already valid, right? The statistics are computed on the fly as soon as we do any new, let's say, any new computation, the statistics are automatically recomputed, right? So if I zoom in, you can see you can start to see the different casing joints here, and in between casing joints we have some connections, right? And the connections lead to some spikes or some, you know, response in the statistics that is not sorry, that is not, let's say, representative of what's happening in the main casing body, right? In the main joints body, right? So what we need to do based on this data is identify where the connections are in order to remove these spikes from the final statistics. And this is what I'm going to do. Next thing is using this interactive joints definition. I'm going to use, for example, the metal loss track, because I know that these spikes in the metal loss are given by the connections, right? So I click here, it says joints computation in progress, is identifying the connections, and and elsewhere is setting joints, right? So here you can see in there is a joints track. Let me zoom in so I show you. Can you see some numbers? This is the number, the casing number in this well, right? So, and there is some color coding, right? So green means lower than 20% penetration, right? Some red values here, yellow is between 20 and 40, and so on, right? So if you see, there are some gaps in the joints definition, right? For example, there is a gap here. And there is a gap there because when we the line that we set for computing for finding the connections cuts some real metal loss occurring within the casing joint body, right? So and Emerald says, okay, the casing length cannot be that small, right? So in cases like this, we can just define this manually. So I click here on manual, and then I say, okay, my casing goes from here to here, right? So these are all our casing. So here you can see it's coming. There we go. Number 72 now is in red, meaning that this darker red is a penetration larger than 100. So at least 100%. This is a full wall penetration, meaning that, well, if we were looking for a leak, we found it, right? Here, by the way, at the top, let me just remove this, maybe something with different radius. In this case, again, we clearly see a joint in red, meaning 100% penetration. I could go straight there, but the typical way is I would go to the joints table. This joints table has all the statistics. If you see index, this is the number of casing identified here during the interpretation, and then the statistics, right, saying basically where is the top and bottom, the length, and then the internal diameter, average, minimum, maximum, and also the statistics of ovalization, reduction, penetration. And as I said, here we are interested about the penetration, right? So let me, for example, sort this table by descending order, meaning that at the top we will see the 100% penetration. So I can just click here, show this one, right? And in the background, you can see Emerald goes straight to this joint, right? Similarly, if I open the cross section, you can see now where this maximum penetration occurs for this joint. So you can see in this case, the leak in the casing is seen by two fingers, right? Is seen by two fingers. The leak is here, right? Actually, another thing we can do is to see this data in 3D. I'm displaying 3D. 3D, we can see the 3D joint by joint. So here is organized by casing joint, the joint number 72. For example, let me increase the radius gain like this. And here you can see that this particular joint, so this is the leak, okay? But this particular joint had a number of lower percentage penetration, right? The only one with 100% is this one, but then this one is this joint is affected by penetration, right? So it's possible to toggle like this and see other joints. This, some joints may not have anything, so this is joint number 70. You can see, so you can see each casing section and identify visually identify the leaks, right? And this is quite interesting to know where to, for example, imagine that you want to take some measure to set a straddle or something, then this is quite useful to do that. Okay, so using the multi-finger caliper, I think we are now quite certain where the leak is. I'm going to click OK here and go back to the main Emerald interface. And now the data is being, we process all of this in the MFC processing of Emerald. This MFC processing is pretty much a separate window. And now you can see all the results are ported into the main Emerald interface. So now, at least from the multi-finger caliper side, we have identified where this leak is, right? But also the objective for this webinar was to see a bit of spectral noise logs. So we are going to load some spectral noise. But first of all, let me give you a quick intro. So what are these tools? What are spectral noise logging tools? Well, these are passive acoustic tools. Passive in comparison to what we do in cement evaluation that are active. You know, in cement evaluation, we send a sonic or ultrasonic wave, and we study the signal that bounces back after, interacting with the casing, with the formation, with the cement, and so on. This is passive, meaning that we don't send anything. We just hear, right? We are here spying. Imagine that you want to spy. You want to spy on your neighbor, right? So you put your ear in the wall. Don't make any movement, any sound, and then just hear, right? So this is the way you do it. So you can do it through using one microphone or multiple microphones here. So and then these microphones are called, actually they are called hydrophones, like a microphone that can measure under the water, right? These are piezoelectric transducers, right? So the piezoelectric transducer here, one or two receives a pressure wave. You know, piezoelectric is capable of transforming a strain, a deformation into an electric signal. The data, well, is conditioned and so on, is moved to the digital domain, and what we will do is a fast Fourier transform, and we're going to move to from the time domain to the frequency domain. Here we'll end up with the amplitudes for different frequency extractions. Each frequency is this K, right? So here you can see, again, one or two hydrophones. Sometimes you want to have more than one. Imagine this is the same as a DJ. When you are playing music, you know that you can set gains to the different frequencies. If you want to hear more the bass frequencies, then you can increase the gain of certain frequencies, right? Well, this type of having multiple microphones is good for that, right? So one microphone may be focused or may have the gains set to handle the low frequency range, and the other one the high frequency range, right? Because in the well there are different sounds, right? So this type of tools are, for example, here this is a tool string that contains two spectral noise logging data. And then depending on the objectives, for example, if you are after a leak, you may definitely want to to add other tools, right? So the best friend of the spectral noise logging tools are the temperature measurements, right? The temperature and noise can see or hear or feel behind the pipe and inside of the pipe, right? So combining both is a very good option. Also, flow spinners, flow meters, right? In case you have a leak, right? The spinner may detect that as well. So how are these measurements? As I said, if you want to spy on your neighbor, you put the ear on the wall, right? And you don't make any sound, right? If you put the ear, but then you start, scratching the wall, you're not going to hear anything, right? Same happens in the wells, right? Imagine you are, the tool is moving here. The tool seems to be magically floating in the middle of the casing, but this is not what's going to happen, right? The tool will be on the low side of the pipe, also the cable, right? So as you move, it will be like you can imagine the scratch, right? The metal to metal scratch. So the acoustic wave would be, of a high frequency, and it's not going to be characteristic of the what's going on inside or behind the pipe due to fluid movement, right? But now if you stop and you record a station, right? Now you can see that the amplitude decreases, right, compared to here, and also the amplitude, the frequency structure of this noise is completely different. Now if you make a station stop and you listen, that now you can hear what's going on inside or and behind of the pipe, right? So then if you move again, of course, and here you can see periods with sorry, tool movement, stations, tool movement again, a station again, right? So you get the point. So in essence, spectral noise logging data is recorded in a number of station stops. So this is a typical program. First, we would go, we would run in hold as a continuous down pass. This continuous down pass is very good for temperature, for example, to let's say pinpoint where the leak can be. And then as you go up, okay, you can record the noise as you go down if you want, but the down pass, you can use it to actually record the temperature. That's a better strategy. And then as you go up, you see you move the tool, and then you record, for example, a 30-second station, 41 minute, depending on the objectives, and then you move another, I don't know, 3, 4, 5 meters, and then you record another station. So finally, the file may be composed of hundreds of stations, right? And then something that Emerald allows you to do is to go from these hundreds of stations. So this is basically, let me show you the next image here, the spectral data versus time. This is in the horizontal, this is the time scale. Emerald will allow you to go from this versus time to the versus depth data. In this webinar, we are not going to do it because I need to finish in like a few minutes. So in this webinar, what I'm going to do is just to load a process versus depth spectrogram, right? So I'm coming here to main and load, click on add, and then I'm going to load this NTO tool from Sondex. This tool goes up to 12.8 kilohertz. You can see as soon as I load it, the data is identified as noise because it contains a depth and then a number of spectral channels, 128 channels in this case. And I'm going to import this. And then there we go. And then here you can see that where is the noise. Let me just remove some of this data, and then I'm going to put it here. So there is the noise data was not recorded for the whole well, but seems like the noise data was recorded only after the MFC had pinpointed, or maybe a temperature had pinpointed where the leak may be, right? So let me just modify the color scale. I'm going to save, let's say, from 25 to 45 decibels. There we go. So the noise data and let me just zoom in a bit more so you can see. Remember, this is the joint 72. Here, the casing joint 72 is the one with the leak. You can see based on the color scale. And then the leak was here, and this is where the noise is occurring, right? So something else, the Emerald computes what is the energy. So this is the normalized energy. So the peak energy is occurring at the level of the level of the leak, right? So in this case, you can see that we have an integrated analysis based on noise data, multi-finger caliper, both pointing towards the same, let's say, depth for leak detection, right? This is all complemented by tables when you apart from the 2D or 3D visualization, the cross sections that I show you. The results are you can find the results in a tabulated way that you can quickly see where your 100% penetration is. You can see the penetration summary based on histogram with number of casing joints versus penetration level, so you can quickly assess the general well condition based on this statistics, right? So I think this is it to me. As far as I understand, the last 15 minutes were meant for questions, so we are exactly on time for the questions. So if you have any question, please feel free to ask me now. Otherwise, thank you for your time today. And then, yeah, Masin, please.
Yes, thank you for your time, Nicholas. Was really informative and really, let's say, fruitful webinar. Okay, so if anybody have a question, can jump in, open the mic.
Hello, Mazen.
Hello.
Hi, Nicholas. Hi.
Hello.
So I have a question, and that's regarding the nominal thickness. What do you consider as nominal thickness? Is it the manufacturer, like the thickness, or you have another method for calculating a nominal thickness and then calculating the metal loss from that?
Good point. Yeah, great. So in Emerald there are different options because, as you correctly said, the manufacturer has a nominal thickness. We know the ID, we know the OD nominal values, and from that we can calculate. So here, when you go to joints, you can see the different options, right? By default, the statistics are based on the nominal ID, right? Then from the catalog, right? You pick the 7-inch casing, 29 pounds per foot, then it will say 6.814, right? But then you know that there are thickness variations, right? The joint, the casings are not all the same, right? So instead of being based on the statistics, instead of being based just on the nominal diameters, they can be based on some statistical value across the casing, right? So, for example, you can consider the median ID measured in the casing, and that will be taken as your new reference value, right? The other thing you could do is if you have a baseline multi-finger caliper. Let's imagine that you complete the well and run a baseline MFC, and you consider that baseline is with the well in perfect conditions, then that may become your nominal as well. Okay, so those are the options.
Thank you. My second question is regarding the centralization process. So I don't understand exactly what do you mean by how to exclude points from centralization, and I mean, how this approach works? I don't know exactly.
Good point. Okay, so actually,
Thank you.
this yes, I don't have this in the slides, but something that I also could recommend you to do is from our website, from the Kappa website, to download this book. The Kappa case or login book is for free, right? And then you can you can go deeper here. So in the centralization, basically what we want to do, as I said, so the eccentric data, right, is caused because we are measuring from the center of the MFC instead of the center of the pipe, right? So so during the centralization, what we do is actually we recalculate what's the actual center of the pipe for every cross section, right? And to do that, we use a perfect circle or ellipse, right? We fit all the points using a perfect circle or ellipse. But the reality is that at different depths, we will find penetrating issues, the positional issues, like in this case, right? So you can see many points fall in the shape of the perfect circle, but then these two points in yellow can see, some erosion, corrosion, or whatever. So these points must be excluded from the fitting, right? So you can see here the difference between the centralization with the having excluded these two, or the centralization without having excluded these two, right? So in multi-finger caliper, with here, when before centralizing, it's good for you to go through the log and see, for example, a quick way to see if I can right-click, for example, at this depth, at the depth of this penetration, show values here, and you can see that this penetration is this is seen by a number of fingers, right? It's seen by here. This is the radius versus the finger number, right? So it's seen by the finger number 35, 36, 37, 38, right? So at least I should remove these 4 fingers from exclusion. So this is a good option to go through these fingers, the log, and identify and let's say have a quick idea of the size and shape of your defects, right?
Fair enough. Thank you.
Yes, I believe Vuldan have a question. You can jump in, Vuldan.
Thank you very much, Mr. Mazi.
Vuldan, you can unmute yourself.
I'm sorry, I was speaking. Yeah, basically, I have not question, I have a comment. Thank you very much, Nicholas. You did a great presentation. I really enjoyed. Kappa is doing one of the best and one of the powerful software. I don't have comments on this software and Emerald itself and interpretation. I just have small comment on MFC application. Yes, MFC, it's quite good technology. It's like always direct measurement, but it has also some limitations. First of all, you're always limited by scale. So if any scale present inside the well, it will be quite difficult. Second limitation, you cannot run MFC in coated tubing. It's also a bit challenging. Third one, it's limited azimuthal coverage, because you have fingers and fingers are not covering 100% of your surface, internal surface. And if you run MFC 2 times in same well, 2 times it might be different results, because finger position every time it will be different. And the last comment, MFC, it's quite good if you want to see any internal corrosion, but for external corrosion, unfortunately, you cannot catch it. Yep. Yeah, that's it from my side. Thank you.
Good. Yeah, I agree. This is also regarding the coverage. again, I didn't include every single point here, but here is in the book that you can download from our website is what is the circumferential resolution of MFC measurements. So for example, in a 7-inch casing, a 40-finger caliper, you only cover like 13%, right? The fingertip is in touch, is in contact with 13% of the internal surface. So as Bildan mentioned, you are not touching the whole circumference, and this you can miss if there are some small holes. They can be missed, right? So you always need to remember that this is, statistically, if you have a homogeneous deposition, homogeneous pitting, well, you're going to catch it, you're going to get a good sample. But you may as well miss if you have a small hole that falls in between two fingers, you may miss it, right? Regarding the coated, so I've coated casing, coated completions. I've done a few jobs. So one of the fears is the MFC itself scratching the pipe surface. And you need to remember that the contact force of the MFC is only 1 pound-foot, so it's barely in touch. So the finger itself, I don't think that's the responsible. What I worry the most is about the centralizers, centralization force, or even the cable, or if you have to use coiled tubing. Of course, that puts the completion at risk. But if it's a vertical well and you can manage it with maybe not a 40-pound-foot centralizer, then you are in a better condition, right? So yeah, those are my comments.
Thank you. Any more questions from the audience or attendees? Okay, maybe I will have just like, I have a few questions actually, okay, but time is mostly finished. Okay, so I will just want to ask, in this document, there is this figure number 8C15, okay, in the document, yeah. 8C15. Yeah.
Yes.
And there is this this point in conclusion, if a recalibration was applied after then a new second, can you elaborate a little bit more about this one?
Good. So if you remember what we did in this case, so first we did the centralization, right? Then after we centralized the data, we realized that some fingers were measuring consistently lower and higher values. So this is that we needed recalibration, right? And then we recalibrate, and then this is the final data, right? So this happens. This, if we go back to the when we centralize the data, we need to exclude some fingers, right? And the fingers that are excluded are typically, the fingers that show the maximum or minimum value, right? That show the actual penetration. But what I mean in that image is that in cases like this is an MFC, for example, with a very bad initial calibration. When the level of stripiness is so big, you see some fingers that consistently measure very large values, very low values. This doesn't talk very well about the calibration, right? And then when you exclude fingers during the centralization process, then the fingers that you are excluding, automatic excluding, may be, well, this type of the fingers that are there, values that are there, just because the initial calibration is very, very bad, right? So what I mean here is that one option is, so first, we would centralize the data, then we will apply the recalibration, right? And then if the recalibration shifts the magnitudes, right, that you come here and you see the shifts here in inches, if these values are very large, what you can do is to go back to the centralization, delete this initial centralization, we are deleting this initial centralization and reapplying a new one, right? And the excluded values will already take into account the recalibration that was applied initially, right? So this is for cases with very bad initial calibration. You could centralize, recalibrate, and then delete the initial centralization and centralize again.
So we need to delete the initial one.
Yeah, you can. Yeah, you delete it, or here at the bottom just recompute all, and then this will recompute. Yeah.
So if we recompute all, it will, like, let's say, override.
Yes.
Yeah.
Yes. Yes.
The previous one. Okay. So I believe the time of webinar is finished. Okay. If anybody have any question, he can drop us email or drop Mr. Nicholas directly. Okay. Thank you, Nicholas, for your time. Okay, really appreciate it. Really informative webinar, and looking to see you in the, I believe, September.
Okay. Thank
Yes.
you, Masin, for the invite. I appreciate it. Great to be here, and see you in the next webinar.
Yes, see you. Thank you, everybody.
Thanks.
And by the way, just one last thing. We can share this chapter 8 and the example from Kappa when we send the video. It's okay?
Yeah.
Okay. Okay. We'll send by.
Okay.
Okay.
Perfect.
Thank you, everybody.
Thanks.
Have a great day. Bye-bye.
Thank you very much. Bye-bye.